This is Chapter 8, Problem 16. We're dropping a block of 0.7 kilograms onto a spring with a spring constant of 400 newtons per meter, and the spring is going to compress 0.19 meters. The first thing we need to do is we need to figure out the work done by the block on the spring and then by the spring on the block. Now the language here can get really confusing. So what I'm going to do is I'm going to start by looking at just the spring. We can calculate the work done by the spring, and that's equal to 1/2 kx initial squared minus 1/2 kx final squared. The spring was initially unstretched or compressed, so that means that the initial compression of the spring, x initial, was 0. That means that the work done by the spring is equal to minus 1/2 kx squared, or that's equal to 1/2 the spring constant 400 multiplied by 0.19 squared, and the work done by the spring is equal to negative 7.22 joules. Now that's the work done by the spring on the block. Okay, the work done by the spring on the block. Another way to think about that follows. Recall that the work done is equal to the change in kinetic energy. The block is falling and then hits the spring. So the block had kinetic energy, and then as it compresses the spring, that kinetic energy goes to spring potential energy. So that means that the change in kinetic energy, or Ke final minus Ke initial, the final kinetic energy of the block is 0, which means that the work done by the spring is equal to minus Ke initial, which means that the work done is negative. So this is another way of seeing that the work done by the spring on the block is negative. The work done by the block on the spring is going to be equal and opposite, so that means that the work done by the block on the spring is equal to minus the work done by the spring on the block, so that means that that's going to be equal to a positive 7.22 joules. Okay, so the minus sign and plus sign can get a little tricky. The spring is doing negative work because not only is the spring being compressed, but also the spring is slowing down the block. So two different ways of looking at it. Now we need to figure out the height that the block is released. So that means we're going to use energy conservation. The final energy is equal to the elastic potential energy, 1/2 kx squared, and the initial energy is equal to potential, which is mgh. Now notice that this h is going to be a little bit different. H is going to be made up of the height that the block was above the spring initially, plus the compression of the spring, 0.19 meters. We have to set our gravitational potential energy point equal to 0 somewhere, so I'm going to set it equal to 0 when the spring has been completely compressed. Now setting up our equation, we have 1/2 400 times 0.19 squared, and that's equal to 0.7 times 9.8 times h plus 0.19, and that means that h is equal to 0.86 meters. On the last step, we're going to double the height above the spring. So that means that now h in our conservation of energy equation is going to be 2 multiplied by 0.86 plus however far the spring is compressed. So now our equation is going to look a little bit nastier. It's going to be the elastic potential energy, 1/2 400 times x squared, where x is the compression of the spring, and that's going to be equal to mgh, 0.7 times 9.8 times 1.72, which is double the height of 0.86 plus x. You're going to have to solve a quadratic here, and I'm going to leave you guys to it. You should get that the compression of the spring is equal to 0.26 meters, or just 26 centimeters. Okay? All we did was energy conservation. The initial energy was all gravitational potential energy. It's double the height that we started at plus the compression of the spring. Remember, we need to set the 0 point for our gravitational potential energy, and I'm setting that 0 point to be when the spring is completely compressed. So you need to add those two heights together, and you set that equal to the final energy, which is going to be all spring potential energy.